Happy Tuesday. So we are working on getting caught back up here. I think we're pretty close to where we need to be um, in terms of content. Again, we're not getting super deep into these topics here. I think I've said that way too many times. I apologize. I'll keep saying it. But we're introing the topic here, and then we'll come back to it. So we didn't get to search trees last week. We'll talk a little bit about search trees today, and then we'll leave the sorting and selection for Thursday. And I think that will get us back up to where we need to be. On 4.8, we should be able to cover everything we need to when it comes to ethics in terms of introing the topic, getting you thinking about it, talking about a professional code of ethics, which is super cool. And then I think on 4.10, if all goes well, we'll also have that for final project work time. Again, my goal is to, ideally, you're done by 4.17 and can focus on your other finals and not have to sweat it and worry and stress over things like that. So do plan to come, right? And work with your partner or organize with your partner where you're going to meet here. Because I'm assuming everyone thought they had these afternoons booked here before they realized they didn't have to show up in person, those sorts of things here. So if you're a bad partner, just don't be a bad partner here. That'll work out well for us, because one of our outcomes is to be able to do this as part of a team. So that is mandatory. Apparently not everyone got the memo, so I'm assuming they didn't listen to the recordings here. So I'm preaching to the choir, but I'll put out an announcement here. So if your partner fires you because you didn't do any work, you fail the class, because this final project is 40% of your score, okay? And doing this by yourself is not an option. So I'll put that out in a little announcement, remind people you cannot pass this class with an individual final project. It just doesn't happen here, right? Because one of the things we need to be able to assess to see, are you progressing on your journey of learning how to write code, is can you work with the team here? So this is sort of a sticking point. And the downside is if you fail this class, they only offer it once a year, and I'm the only one who teaches it. You're stuck with me again next winter. Just don't, okay? Just get your work done. I get it, you know, it's tough when we have lives, and be a little bit flexible here, but you can do something here and you can meet with your group. So 4.10 we'll probably have set aside for final project time. We'll assess that next week when we get there, but we should be able to get through everything on Tuesday. In terms of a lab, there's not too much to do for search trees. We can use them, but like writing our own is, we're essentially copy pasting out of the book here. For sorting and selection, we can do a sort. We did one already. Depending on how you went about our project here, where we kept things in sorted order, that was essentially an insertion sort. We're finding where does this piece go in the list here and putting it in that spot here. So we'll look at two basic sorts. They're not much fun after I've talked about them for you to write the exact same code. So there's not too much there. So I'm hopeful we can get to should we do ethics early so we can do our ethics lab on 4.8? That way we can give you lab time on 4.15. The ethics lab is quick. So even if we have to do ethics lab on 4.15, it's 15 minutes. It goes pretty quick here. A quick little write-up. So we'll have lots of time in lab and 4.15 and 4.17 to work in your final project. I'll be here. I've got a class after this one, so I don't get to go home early, unfortunately. But I can answer questions, get you pointed in the right direction. Again, give it a good half hour to hour of effort trying to get yourself unstuck. Like learning how to Google better than the average bear is definitely a skill you want here. But after you get stuck, come ask me. Most of the time, it takes me 5 minutes or less to get you unstuck. So, you know, after an hour, it's worth having the quick conversation with me. We can do a screen share most any time. I've got a pretty flexible schedule. We can set up a time to do a screen share. You don't have to wait for a Tuesday or a Thursday and lose 5 days of working time if you've got questions there. And then on my birthday, unfortunately, I have to be here, and I have an 8 a.m. final for the morning class. Just the worst here. But I'll take a nap after that before this one at 3 p.m. So I'll be napping in my car probably. But then 3 p.m. we'll show up, and our 8 teams here will present their final project. We're all doing the same thing. It's a little bit boring. I apologize. And all the results should look very similar, but it's interesting to see how other people approached it. Again, I've given you some ideas here. Hey, we have to have classes, we have to have these functions, but how you display your results, and some people used some fun little libraries for looking at some pretty results. Someone made graphs one time. So they're like, hey, I can graph this stuff. I was like, yes, we know how to graph things. That's a fun way to show your results too. So lots of options there. Hopefully it's not too bad. It's 5-minute presentation, maybe 10 if you talk a whole lot like I like to talk a lot here. With 8 groups, we'll be out here in less than an hour. You can have the rest of your afternoon free. And should be a lot of fun. So I'm looking forward to it. This will be probably the last time I see y'all data scientists here. I haven't taught any of the 400 level classes in a while. They hired some other really good full-time tenure track profs who are specialists in that sort of massive data thing, so I don't have to teach that class anymore, which is fine. It was fun, but so I probably won't see you again, but keep in touch. Look forward to seeing your senior design projects when you get to that point. Keep in touch and let me know what I can do. So we're almost done, believe it or not. So it's been a lot of fun. So I think that's it for the syllabus. And I thought we should change it up today. And I should do my code on the blackboard. Be nice and old-fashioned here. I hear you learn better if we do things on the blackboard, right? It is my April Fool's Day joke. I tried. No, that's dumb. But believe it or not, when I started here in 2016, the guy, super nice guy here, but his philosophy was to give people paper tests in the coding classes. Because if you knew it well enough, you could write it on paper. While yes, that's true, it's also ridiculous. And he would mark them down for missing like semicolons and curly braces and things. It's like, the computer tells you if you're missing that. Like, you don't have to. It's like, no, they know it well enough, they can get it right on paper. It's like, yeah, okay, sure. But I don't do that anymore, so thankfully. We did try it once, because I think it's my first time teaching a class. I'll try it. It was awful. It was just awful. So anyway, let me fire up PyCharm here, and we're going to look at a binary search tree. So we looked at this idea of trees, n trees with some number of children. We looked at binary trees, whether you have just a left, just a right. We looked at starting them as linked trees when we started our heaps, our priority queues, and then we realized, hey, that just got to be a big mess here. It's easier to keep it in an array. And now we're going to jump back to the links again, because if we can't guarantee that sort of full structure where every level of the tree is full, then I'm going to have tons and tons and tons and tons of empty space here if I have like a left child and a right child and a right child and a bunch of gaps over here. So keeping that linked structure is going to work better for us if we're not maintaining some sort of balanced full structure here. And when you get into tree theory, there's all sorts of really smart people who've done really cool things working with trees to keep them in some sort of form like that. That's a lot more trouble than we want to get into right now. So we're just not going to. So we're just going to do the easy thing here. This is binary search trees. Welcome script, got that one. Virtual environment, cool. So let me go copy paste our tree for a minute. Because I need the node class is what I really want out here. PyCharm on this computer just sucks. It like crapped out of me this morning. It wasn't working. It was bad for my demo, but that's okay. We're getting there. So let me go find the, I think it's just this whole laptop is slow. I have to get my other one replaced. All right, so let's go to trees. We'll go look at our linked tree that we threw away. Binary tree, linked binary tree. Okay. And we'll throw that one in here. I should probably cite my source here, right? Model good behavior. Okay, so we got our linked binary tree. Now we're going to use this sort of as a wrapper here. We're not going to use this one directly because I want it to be a binary search tree, which gives you less options here. So you don't get all of the same things. With the binary search tree, you don't get to say, hey, add the same to the left or add the same to the right. Because the way that a binary search tree works is it keeps data in a specific form, a specific structure, so I can get good performance of things. So the idea with a binary search tree is that I've got a relatively simple rule we're going to follow. So I can't even draw. I don't have drawing on this one here. How do I do my nodes? Screen snip tool. There we go. Snip tool. There we go. I can draw on a snip tool. We can do that. Sure. New. I'll just capture all of that. Why not? I'll just draw on this thing here. Really? That's what it gave me? Okay, sure. So, got our first node here. Right? This is the root of our tree. Anything can go here. doesn't matter what goes in the root here. So whatever first value we have for our tree can go here. If we want, we can handle all of our null checks, and we can start empty, and sure, it's not the end of the world. It's just a little bit more code for us to manage here. So maybe we start nothing here. So our root then here can start off as null here, and eventually we'll come back and we'll go add something in here. So when you add your first item, if you have no root, you add it to the root. Okay, so what's a number we should add? 4. Okay. From here on out, anything less than 4 will have to be on the left of it. Anything greater than 4 will be on the right of it. And that's our rule for a binary search tree. That is the rule. That's the only rule we have to follow. So anything less than goes to the left. Anything greater than goes to the right. Okay, so let's go add another number. 12. Okay, is that less than or greater than? Greater, so it's going to go to the right. I don't have a right child, so we're going to add a right child here. We put a 12. Let's add another number. 2. Okay, is that less than or greater than? All right, so it's going to go to the left. Do we have a left child? No. All right, so we're going to add a left child. Cool, let's add another number. 6. All right, is it greater than or less than? All right, it goes to the right. Do I have a right child? Okay, am I greater than or less than my child now? Less. Okay, do I have a left child? No. All right, so now I have a left child. 6. Okay, give me another number. 18. Greater than or less than? Greater, don't have a child. 18. Give me another one. I heard 3 first. We'll do 3 and then we'll come back for 16. So 3, less than. 3, greater than. All right, now we have a child here. Okay, 16. Greater than. Greater than. I already have the child. Less than. Now this one gets a child. 16. How about 5? All right, greater than. Less than. Less than. Go to the left. 5. All right, how about like 8? Well, greater than. Less than. Greater than. 8 goes over here. So at any point in time, everything to the right is bigger than you, everything to the left is bigger than you, and it's a recursive definition, right? So the tree rooted at 12, everything to the left is smaller, everything to the right is bigger, and it just goes all the way down here. Now, adding is not so bad here, and assuming we add things in some sort of distribution that's kind of randomized here, and it's not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, where I would get that chain of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of left children, we'll have somewhat of a close to balanced structure here. Now, it's not guaranteed. So in terms of n items here, how long is it going to take me to see, do I have an item in a tree if I can cut it in half every time, or close to half every time here? Log of n. Assuming we can get close to half, right? At some point the math doesn't work out here. But in general, if we get somewhat of an even distribution, we add these things in here. So we'll cut it in half. Go to the right, go to the left, cut it in half, cut it in half, cut it in half. So we can get log n performance of getting values or searching for values in our tree here. And now this is where, back when we did tree traversals, does that ring any bells? We started back with the n tree. I have to go I can go all the way down, or I can go one level at a time. We looked at the 2 different operations here. There's some other ways we can do these things here, and now the names of them actually make sense that the book used. There's an in-order traversal. The in-order traversal works for something in a binary search tree form because it says, okay, go to the left, go to the center, or do your own node, and then go to the right. So it's left, center, right every time here. So starting at the top here, we're going to say, okay, start this algorithm that says left, center, right. So starting at 4, we get a left, center, right. The first thing we do is go to the left. All right, so now we're at 2, and we go left, center, and right. Now at 2, there is no left, so left is done. Now we can do the center. Now we actually process ourselves. So now I spit out the 2. We did that one. Now we go to the right. So now in our call stack, right, now we're at 3. We go left, center, right. There is no left. The center is 3. We print the 3. There is no right. This call comes off the stack. We're back at 2. We did the right. This one comes off the stack. We're back at 4. We did the left. Now we do the center. We process 4. Now we go to the right. All right, so now these 2 are off the stack here. We can erase them completely here. The next call on the call stack then is 12. Right, at node 12, we're going to go left, center, right. All right, go to the left. Well, that's 6. Left, center, right. All right, well, that's 5, right? I think that's a terrible 5. 5, left, center, right. All right, well, there is no left, center, but now we get 5. There is no right. This one comes off the call stack here. Now we're back at 6. All right, we did left. That one's done. Now center. We print 6. And now we're going to recurse, right? This recursive nature here back to the right node. Now 8. So 8 goes on the call stack. Left, center, right. There is no left, right? Center, we process the node. And we go to the right. There is no right. This one comes off the call stack. 6 is done. This one comes off the call stack. Now 12, we did left. Left is done. Now the 12 comes out. And then that was center. Now we go to the right. So now 18, left, center, right. Here, 18 says, okay, left, center, right. Left is 16. Left, center, right. Left has no left. 16 gets added, printed out here. There is no to the right. This one comes off the call stack here. 18 now, we did left. Left is done. We do the center. 18, there is no right. That one comes off the call stack. 12 is done. 4 is done. So we've processed an entire binary search tree in order using a recursive function that says, okay, go left. When you're done with that, do the center node. When you're done with that, do the right node, do the right child. So this sort of in-order traversal makes sense if we're a binary search tree. We get the things out in order, and we can traverse it very quickly here. So we keep things in a sorted order here if the order needs to be sorted. Right? It's not just a generic list that the first thing is first and the second thing is second, the third thing is third, and you can put things in any order. It's if I have stuff that has to be sorted here, I can put it in this particular form, I can find it very quickly, and I can get it out very quickly. Now our heaps were really quick here, our priority queues, but we couldn't really find things in there. I didn't really know, hey, should I go left, should I go right? Because it just was, hey, I'm gonna have 2 small children, or 2 bigger children, right, whatever our rule was, and 2 more and 2 more and 2 more. So we couldn't really find things now. So finding in a binary search tree is really fast here. I can put things in really fast because, again, we take advantage of, we're probably balanced here, and some sort of, we'll have close to the same number of children on the left and on the right. And if you keep balance all the way down here, we'll be very logarithmic based, right? Because the number of levels, the height of our tree is relates to how many items we can store. So we get that good performance here. So we get, for adding, you can get log of n, assuming we get some good distribution. And this is when you get to the more advanced trees, you look at methods for how do you make sure they stay balanced here. There's 2 really common ones you'll get to, the red-black trees and AVL trees. And I did it 20 years ago and have forgotten. And I would just ask the chatbot nowadays or go look in the book how you do those. I just know they exist and I'm happy. So smart people figure out how to keep trees in balanced form. We don't bother with that at this level. We're just saying, okay, sure. If you do it right, it works well. Right, so add is log of n here, then find, again, is log of n, because we're cutting it in half here. Now remove gets to be tricky here, but smart people thankfully figured this out for us here. So to remove something here, we have to replace it, essentially, right? So I can't just take the 12 out and have a gap here, because I have to have a value here. So what you do is you replace it with your largest child, because the largest child will be greater than your left child, right? And it will be less than your right child every time. So if I were to replace 12, to find your largest child, I go left and then as far right as possible. Or your guys are as left and then as far right as possible for your direction here. So left is going to be less than me, and then as far right on that node as possible, I'm going to replace. I'm going to grab and replace. So I'm going to find 8, and I'll be able to replace the 8. Now, taking 8 out of here, if 8 had children, I might run into problems here, but I know it will never have a right child. Because if it had a right child, I would have gone farther right. Right? Because there would have been a larger child for me to go replace myself with. So at most, it has 1 child. And if it only at most has 1 child, I can put that one in its place guaranteed. Because say I had a 7 over here, right? If I were to have a 7, it's to the right of the 6. It has to be bigger than 6. It can go to the right of 6 here. And maybe 7 had other children here, right? This could have like a 6.5 and a 7.5 or whatever. It doesn't matter here. I just take this node and drop it in place of this one here. So if I have a child, drop it in. If I don't have a child, Sure, I'm done. I just remove it here. So to remove it, we have to remove the links. So writing the code for this gets to be a bit tedious. Honestly, I'm not even sure if we want to bother writing the code for it because the textbook has it, and it's really boring to copy paste this stuff. We'll see. Maybe we will. So I will just take this 8, drop it in place of the 12, right? Because we want to remove 12. So we're going to drop the 8 in. And then if there's a child, we'll replace. And then we'll fix these links here. So, hey, my parent's right child now, you now point to me, whether or not it was a none, because I didn't have a left child, or I had a left child, here's my left child node. Here's the node in the tree, right? These nodes have links. And then if I have a left child, hey, your parent is no longer me, right? Your parent was my parent, right? So we have to fix those links here. So this works out here. Now, if it doesn't have a right child here, right? If 6 didn't have a right child, we pretend these ones didn't exist here in the tree, and I wanted to pull out the 12. Well, all I have to do is take 6, right? My left child is the largest child I have in my subtree on the left, because there is nothing to the right of it. There's nothing bigger here. Anything to the left of it is guaranteed to be smaller, even if they have right children, because it's to the left of it here. So I would just swap the 6 and do that same, okay, you've got one child or none, swap in. So the algorithm for that is actually really quick and easy. It's to find the next largest descendant, I think is their technical term for it here. So you go left, and then you go as far right as possible. You find that node, and that's always the one you're going to swap out. And that works for no matter what happens in the tree here. Any of these positions we can pull out here, doing it that way. Now, the only problem we have then is if we were to get down to this position where we have a 4 here, and I want to remove 4, because I have no left child. So if I don't have a left child to even look at, then I've got to take my right child, right? So this gets to be a little bit messy. There's a little bit of awkward handling that has to happen in here to manage all of this, where if you don't have a left child and you're removing it here, right, you have nothing to swap in. So it gets to be a little weird here. So like if it was, say, just the 18, so if I have a bigger child here, like a 20 here, and I'll remove the 18, if I don't have a left, if I have a right, I just swap in the right. And so it's not too bad, but it's a little bit of special handling. So if there is no left here, well, then you just take the right child, right? Having one child is easy because it just takes your place, right? So we just drop the 18 out here, put the 20 in the place, say, okay, whatever it had, even if it had left children and right children, that's fine. It goes in this place here. So the only issue we have is with root here. We would just simply replace root with its right child here of 12. And works out relatively well. If it doesn't have a left, well, then we got to take its right. If its right is none, then sure, maybe we just remove the last thing. So we can store things in this tree form. We can get adds really quick. We can get finds really quick. And in turn, turns out finding your largest descendant is still logarithmic based. If we've got this sort of balanced structure that we're kind of hand waving and assuming we have here. So the remove then is again log of n. So all of our performance of this one here is log n here for how quick and how fast we can get these things here. Now what we don't get is instant access to the smallest or largest item like a heap had. Right? With the max heap, we always had instant access to the smallest item or the largest item. To do that, you'd have to walk all the way to the left for you guys to find the smallest, or right to find the largest. So it would be logarithmic to get the first and last item out. But if you only ever want the first or last, you're going to use that priority queue anyway. So as we're adding these tools to our toolkit, hey, if I need to be adding things, finding things, removing things, and I want them in sorted order, this is a really good tool for that. It works out really well here. Now you can do the same sort of thing with an array, but you're going to use, or a list, you're going to use a bunch more space because you don't know how many levels you have, but you can do that same sort of arithmetic. Hey, I know my parent's index is always half of mine minus 1 or 2, and my child's are always this here if I've got those nodes, but the math works out a little funny to know if you even have children there. You have to look and see, is it a none or not? So it's doable without links, it's doable with links here. Both ways can work, just depending on if we're keeping them balanced or not. So I think the more balanced versions of these use the arrays. But we'll leave that to the really smart people to look at. Other ways you can traverse these trees, those other ways we looked at, going all the way deep first, and then coming back up, they don't really make sense for a binary search tree. Because the only really order which it makes sense to do this is in the in order left, center, right traversal. You could go level by level, using the queue like we did. It doesn't really do anything for you though. Like that's just going to look like nonsense because it's just the order we put them in is going to be in that order here. So you still can traverse them the other ways. It still works. It's still a tree. You can do tree traversals, but it doesn't really help you at all. Just the in order traversal works out best for you there. All right. I feel bad saying we should just skip the code, but it's really boring to copy paste from the textbook. Is that wrong? Should we go and write it? I'll really just go copy paste. Like I don't, it's been a little while here. We could try it and see. Okay. Yeah, these like advanced structures, we look at them and, if we were to build them out, yes, that'd be nice. Yeah, we're just gonna look it up here. Should we have chatbot do it and then just look at what the code looks like? We can do that. Let's try it. So what's practical is how you use it more than the code itself here. So this is write a research tree class in Python. What? Yeah, so this one back, it's been a while now, a couple iterations here. Back when ChatGPT had version 3, but you could pay for version 4, the university was like, we should just give 4 to everybody because that's kind of an equity thing here, and they get to manage it themselves and keep data private. And now when you paste information in here, it doesn't necessarily go out to Microsoft's and ChatGPT servers, which depending on what you're pasting in here might be a good thing. They can control some of that data a little bit better. So that's, sort of nice here. Look at that. Okay, this wasn't too bad. Not too bad here. So we're going to get rid of the linked binary tree, and we're going to put this in from UMGPT, and this was our prompt. We said, write a binary tree. Did I tell about the crazy lady on Facebook that I just really shouldn't argue with people? She's like, you really have to research this information yourself. Go ask ChatGPT. It'll find things that Google doesn't have. I about died. Like,
it can hallucinate things that Google doesn't have.
I mean, she's not wrong. It does have things that Google does not have.
Because it makes it up. It's like, lady, I kind of teach computer science. Like, I don't like to throw that at people most of the time because I know I'm an idiot. I just happen to know how computers work. But like when you argue with me, I just like, people aren't actually going to listen, and they're not going to change their mind because I tell them they're wrong. They're just going to think I'm out to get them here because I work for the state and I must be a deep state agent or something here. Like, oh, you're just one of those college profs. Like, lady, I make computers work. So I don't know. Anyway, so our node here. So our tree node, right, has the value itself. I usually call it value. Sure, we can call it key. It has a left. It has a right. We don't even have parent here. That's fun. So there's no parent linking. Sure. So when we create ourselves, our root is none because we don't have any items. To add something, right, you give a given key or value to add here. If the root is none, now we have a root. If it's not, now we do our insert recursive process here. That says, okay, if you're less than, go left. If you're greater than, go right. If I do have a left and you're less than, well, then I need to recurse going down a node. So I do have a left child, repeat the process with my left child. Here, so take my node left, here's the key I'm adding. So it just recursively says, okay, you're less than, go left. If you have something there, recurse and go left. If you're less than, you recurse and go left until it finds one where you don't have a left and it can add it in, or you don't have a right if you're greater than, right? Now, with this, you'll notice we don't handle duplicates. That screws things up because it breaks the rule. If you're the same value, you can't go to the left and you can't go to the right, right? It just breaks things. So this is a set sort of structure. We don't have duplicate values. With this one, I forgot to mention that earlier. So then for searching for something, we just do a search recursive. Hey, did we find it here? Yes, we found it. If not, then hey, try going to the left. If it's less than, try going to the right if it's greater than. And if we get to one that's a none, I ran out of nodes. Nope, I didn't find it here. So our base case is I ran out of nodes, I didn't find it, or the other base case is I did find it, good news here, right? Otherwise, we just keep on recursing, less than to the left, greater than to the right. Keep on going here. And then this in-order traversal here does the left, center, right. Recurse on the left, do the center, recurse on the right here. And this just goes and I think I missed a return here, right? Result, return. Oh, okay. No, so it uses this result here that we're passing in the result list every time here. That's what it is here. And because it's mutable, we can add to it. Isn't that fun? And then eventually we'll go and spit these things out here. Okay, this wasn't so bad. We probably could have written this code in half an hour here without too much more trouble, right? But you can see we get things in order here, if it exists or not in our tree when we put things in. So what we get in terms of the public functions here, we get an insert and we get a search, right? Eventually we'll add a remove, right? And that's where we have to do that. So we could ask it for the remove function, right? Add a remove function. We should add that in as another prompt here, right? Probably wherever we put that remove function. GPT, prompt, remove function. Wow, this was a lot more code than I thought. Look at that. It added other stuff we didn't even ask for. It wants the min value node here. Do we need that? Okay, sure. Define min value node. Yep, okay, so it wants to use that one. Remove recursive, and the min value node. Okay. So to remove something, you call the recursive function. Start at the top, let's try and remove it. If we found it, great, now we're gonna go find our greatest left child or whatever happens to be here. So to remove recursive, if we got to a none, there's nothing to remove. Didn't work here, right? Didn't have that value here. Which this is a little silly. If it's none, return node, but node is none, so returning none. I would have just used the word none here, but that's okay. Chatbot's smarter than I am, obviously. So if it's less than, recurse to the left. If it's greater than, recurse to the right. If it's not less than or greater than, we found it, right? So this is the other case here. So if we don't have a left, right, then we're going to take this right node here, so remove recursive here, right? If I don't have a right, I'm going to give you back the left here. So if I have a left and right is none, right? So if left is none, I only have one child. If left is not none and right is none, well, I still just have one child, right? So these are the two easy cases. I just have one child, either the left or the right, I don't care which one, grab it back, right? But if I have two children, now I need to find the min value node. Okay, so they're going to the smallest, larger child. Sure, either direction is fine here. So they're going to go to the right first and then all the way left to find the smallest next node, right, in the right subtree. And we're going to go find that one here, this min value node function. Says, okay, let's go as far left as possible here. That's it. But we'll find the smallest one here for any node, really. But if we start with the right node, we'll get the smallest node that's bigger than me because I went to the right. I keep doing the wrong direction. I'm sorry. Here, I should turn around. So once we do that, then I know which node I need to replace with, right? This remove recursive here. So self root equals remove recursive. What? Root? I feel like that's not right here. What? Remove a key. Remove recursively the root. All right, now I want to try this and see if the chatbot even worked here, because I'm a little confused here. I feel like you don't change the root every single time. But let's find out. Maybe this works here, and I'll be surprised. So we added in a couple nodes here. Right? You print them out here, and then let's. What does remove give us something? Remove gives us a. Did I copy paste it wrong? No, that's it. Remove a key. There's no return value. No, nothing happens. It just changes root. Okay, sure. So let's call remove on something here. So bst.remove How about we remove the 10? No, let's remove the 5 here. And then let's print the traversal again here. Here, that should be a 10 and 15 if we got it right here. All right, we got 10 and 15 back. All right, maybe let's add in some more values here. EST insert a 3, EST insert 20 here. 3, 10, 15. It's working.
That might make sense if it's actually you're just changing the root away from the 10 and it's not in it anymore.
But I didn't.
Backtracking.
But so 10 should have been the root.
I mean the 5.
Yeah, we removed 5, which should have been the left child of 10 here. How does changing root make that work? I'm really confused here. Move recursively. Given a node here. Given a node. Oh, it's changing things all the way on down. Okay, so it's changing lots of nodes here. Oh my goodness.
So it's like the heap kind of where it kind of rebuilds the whole
Yeah.
way.
Yep. Okay, because it's changing your left all the way on down. It's changing your right all the way on down. Okay, that's a lot more work than it needs to do. But sure. Yeah, so it's rebuilding here. Okay, that's why that one works. Feels like that's a lot of work here. Right, but because it's left and right based, we're still logarithmic, right? You were doing half, no? So rebuilding? Let's ask it. What's the performance? What's the time complexity? The remove function. Let's see if the chatbot knows. On average, it says log of n on an unbalanced tree. Yeah, AVL or red black trees, log of n, where n is the number of nodes. Log of n. But if it's unbalanced, it'll give you O of n here, because we have to do an operation. Interesting. That's fun. Very cool. The chatbot worked. I guess you're not surprised. I was a little surprised. That's okay. There's so much example code out here for these basic data structures. They've been trained pretty well with these here, which is nice. So cool. So that is our binary search tree, right? So adding log of n, finding log of n, removing log of n, assuming we're balanced. Again, we're kind of hand waving on that point here now. So we can make it perform badly if we give it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if you know, with a decent distribution, it should be okay for now. And then later we'll study what are ways we can keep them in a balanced form. How do I make sure that I have some sort of good tree structure? And they do it relatively quickly here with these fun little rotates. And they like take a tree and like pivot it around. So the child becomes this and this and this. And it's really fun. But it's been 20 years and it's okay. We'll save that for the next class. So this keeps something in sorted order with quick performance. Right? Remember our heaps, our maps were super fast, but there was no order. So if you wanted the values in a sorted order, the map wasn't going to work for us. Our dictionary wasn't going to work because it gets super fast performance by not sorting things, by doing that little bucketing idea of, hey, let me just go take a hash value and see where it shows up, which bucket it goes in here. So we're getting different trade-offs for different structures as we go with these things here. But I think this is one of the first sorted ones we look at after the priority queue, which was essentially a destructive sort of sort. Like to get it back, to get the items in sorted order, you had to build the whole heap and then take it all apart. Right? Because every time we took an item out, you took the smallest item, you had to go down heap again, and down heap again, and down heap again, and down heap again. So that was like n log n, right? Because we had to n times, we had to go grab those things. So this one we can put them in, which is still n log n to build a binary search tree, right? Because n items have to go into the tree. Each time we add, it's a log n operation. But then it stays there, and we can work with it in order, which is nice. So you don't have to destruct this whole thing to work with it in its sorted order. You maintain a sorted order, which is pretty nice. Okay. So that's that one. That worked out relatively well. So I think we're okay then. We can pick up the sorting and selection on the third here. We'll finish that out. We'll look at the insertion sort, the selection sort, the basic ones. We'll play with those a little bit again here and look at why they're super slow. We can do a binary search of a sorted list. I think we did that last semester, right? We said, hey, if the list is sorted, you start in the middle and half your way through, those sort of things. There's some other fun sorts you can look at. There's a really fun YouTube video that puts it to sound, which is fun, of like 13 ridiculous sorts here. So I'll send you the link for that. And then on the 8th, we can talk about ethics. We should have time then on the 10th for project work time, the 15th and 17th just for final project work time. Make sure you get with your partner, get this working here. And then one last thing I have for you is a group eval. I mean, group's a bit of a stretch here, but that's okay. It's still you and your partner here. So we drop this in and show you this one here. So this is for evaluating yourself and your partner. Right? So when you turn this in here, it shouldn't be a surprise to your partner. If they suck, they need to know it ahead of time, that they're not holding up their end of the deal here. I'll just open it up in Word on my side here. But I do want to kind of rain on your parade here. So this rating system of unsatisfactory, poor, average, good, and exceptional, I got to be honest, not everybody's exceptional. Is that okay to say? I'm not going to get in trouble? Please don't just give everybody 5s for everything, right? It's very rare to find an exceptional person in a group project, right? It's okay to rate someone average. They're not going to lose points because you said they're average, right? Most people are average. It's why it's called average, right? So you imagine you're all stats people, you know, like this sort of thing. We fall on a bell curve here, and most people are within the standard deviation of the norm. Right? That's why it's the average here, this sort of thing. So 3s are good, right? Don't feel bad giving someone a 3, and don't feel bad if your partner gives you a 3. Okay? If you are above and beyond the average, then cool. A 4 you should be really happy with. If they say you're a 5, amazing, right? Honestly, I don't believe it if someone rates their partner all 5s. I think they just made it up here. That's fine. So you're going to rate yourself and your partner across a couple different things here. And we've got some nice descriptions here. I stole this from, I forget what school had this posted online, and I stole it from them. It's been so long now I can't find it anymore. But like quality of work, problem-solving skills, teamwork, initiative, communication, and time management here. So rate yourself and your partner across all of those. Add them all together here. It's not a spreadsheet, unfortunately, but I think you can add 6 numbers together. It'll be okay. We'll make it work here for your overall score here. So what you're going to do is each partner will commit their team eval to the Git repository. So it's completely public, right? Your partner will see what you put here. Again, don't surprise them, right? If they're not doing their work, you need to tell them they're not doing their work here, that sort of thing. Don't feel bad if someone gives you average scores, right? And it's okay if you get a poor score every here and there, like, hey, your time management sucked. That's not the end of the world. Like, you're not going to fail the class because your teammate said you had bad time management here. This should be a chance for a little bit of, taking some stock. How did I do? How was I here? And as long as you're not unsatisfactory, you didn't screw your group partner over, and you did your work here, you've put enough effort in that they didn't kick you out of the team here. Like, you can't just show up and have done nothing here. You'll fail the class. You worked along here. We'll be okay. That sort of thing. So we've got time set aside. You all should have had this time open. So please don't tell your partner you don't have the time to come because you did have the time when you signed up for the class, that sort of thing. Ideally, we get it done early here. Again, we've got our commit requirements for the final project. So slow incremental progress here as we're going. Let me go to assignments here. It's per group here. It doesn't need to be 10 per person here. As long as your team gets 10 together, that's fine here, right? 10 different days. It doesn't have to be a ton of work, but we're chipping away at it, working piece by piece by piece. Hey, I've got the structure of some classes here. Great, you can have some functions that are defined but not implemented. And then we slowly start to implement them here. Okay, now I've got my classes down. How do I start part 2? How do I start playing the game? Okay, I'll get started on that and make some commits, that sort of thing, right? So work together, figure out who's working on what here, alternate days if you want it. Getting to 10 should not be hard. We've got 3 weeks to get it done from today. Getting to 10, that's only 5 each in 3 weeks. Here, it's not outrageous, I feel like here. So again, it's across a 3 to 4 week project for 2 people, right? This is a 12-hour a week class because we're a 4-credit class, right? That's 48 hours a person across 4 weeks. It's a 50-hour project essentially, if that. I think we can get it done in less if things went well for you in the class. So that's about all I got for you. We can meet back up Thursday and we'll get to sorting and selection and then finish up with ethics, and then I'll be done talking at you for the semester, believe it or not. It's been a lot of fun. So if there's anything else I can do, let me know. And make sure you put yourself in your groups. I'll check with people, send an announcement out, remind them grouping is not optional here, and you do want to pass this class. So it should go pretty well. All right, thanks, folks. I will talk to you later.